Step into the Coliseum of Cambridge exams. Only the prepared survive. Welcome to this explainer, where we are going to systematically conquer the Cambridge Additional Mathematics Review Exercise 4. If you're studying the 0606 or 4037 syllabus, you know by now that this isn't just about memorizing formulas. It is literally an arena of logic, structure, and intense precision. Today, we're not just doing math. We are dissecting exam strategy. I want you to picture two types of students. First, there's Alex. Alex overloads every answer with raw mathematics facts, writing down every formula under the sun, but providing absolutely no analysis. Then there's Sam. Sam rushes, completely misses the command word requirements, and throws away easy marks. Throughout this explainer, we're going to look at their flawed answers, look at the red pen marks they'd get from an examiner, and transform them into top-tier, full-mark responses. We'll strip away the complex wording of rigorous past paper questions to reveal the elegant mathematical frameworks underneath. By the end of this, you won't be an Alex or a Sam. You'll be a master strategist.
Here is our game plan for today. We have 4 key battlegrounds. First, combinatorics and binomial expansions. Second, unlocking mathematical progressions. Third, mastering position vectors. And finally, our climax, the interception, dealing with relative velocity.
Let's jump right into Section 1, Combinatorics and Binomial Expansions, the discrete start. This is where raw logic is your absolute best weapon.
Okay, look at this question. When faced with a word like algorithm, examiners are testing a very specific skill. Can you handle boundary restrictions? The word algorithm has 9 distinct letters. Thankfully, there are no repeating letters, which makes our lives a little bit easier. The command word here is asking for a 4-letter arrangement. Now, if Sam were taking this exam, Sam would see 9 letters and arrange 4 and immediately just type 9 permute 4 into the calculator, write down the answer, and sprint to the next question. But Sam rushed. Sam completely missed the absolute constraint. The arrangement must start with G and end with T. This is where we need to apply a structured framework. We call it the Peel framework. Point, evidence, explanation, link. Adapted for mathematics. Your point is establishing the exact constraint before you calculate anything.
While there are 3,024 ways to arrange 4 letters with no restrictions, which is the trap Sam fell into, pinning down the G and the T drastically narrows your options to just 42. So how do we systematically get there and secure every single mark? Think of the 4-letter word as 4 empty visual slots. You've locked the letter G into the very first slot, and you've locked the letter T into the 4th slot. Those decisions are permanently made. You now have 2 empty slots in the middle, right? And because you've used G and T, you have exactly 7 letters remaining from the original 9. You just need to arrange 2 letters out of those 7. That's your evidence. Mathematically, that is 7 permute 2. 7 times 6. Exactly 42 arrangements. The explanation is you're working out, and the link is tying that 42 back to the specific context of the word algorithm. It's about stripping the problem down to its moving parts.
Now, let's step up the difficulty. What's really interesting here is how selecting a team of 8 scientists from a pool of 12 ecologists and 6 meteorologists changes when absolute constraints are applied. Order doesn't matter here. A team is just a team. So we're dealing with combinations, not permutations. We have a total pool of 18 people. Now, before we break down the math and see how Alex would overcomplicate this, I have a quick reminder for you. Before we continue, subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, back to the science team. If Alex were solving this, Alex would try to calculate the probability of 1 meteorologist, then 2, then 3, creating a massive confusing web of data, getting totally lost and wasting 15 minutes. We don't do that. We decode the command constraints. Forcing all 6 meteorologists onto the team eliminates thousands of variables instantly, leaving you with only 66 exact combinations. Let's unpack the logic. If there are no restrictions at all, you're just choosing 8 people from the total 18. That's simply 18 choose 8, which gives you 43,758 possible teams. Easy. But if you literally must contain all 6 meteorologists, those 6 slots on your 8-person team are non-negotiable. They are filled. You only need to find 2 more people to complete the squad, and those 2 people must come from the remaining pool of 12 ecologists. So the calculation simply becomes 12 choose 2, which equals exactly 66. Now look at how this brilliantly sets up the final bullet point, at least 3 ecologists. Since there are only 6 meteorologists in existence, a team of 8 must have at least 2 ecologists no matter what you do. So the only possible scenario where you don't have at least 3 ecologists is the scenario where you have exactly 2. And we literally just proved there are exactly 66 ways for that to happen. So take the total, 43,758, subtract those 66 rule-breaking teams, and you instantly get 43,692. No massive calculations, just pure deductive logic that saves you precious time.
Moving right along, Section 2, Unlocking Mathematical Progressions, Pattern Recognition. This is where we see red pen marks transform into green check marks. This right here is a classic Cambridge setup. You must reverse engineer an entire arithmetic sequence from just 2 scattered pieces of data. You are given the 10th term, which we call U sub 10, and the sum of the first 5, S sub 5. Think about the structure. You have 2 unknowns, the first term, A, and the common difference, D. 2 unknowns, 2 pieces of isolated data. The command here is implicitly asking you to build a bridge between them. This is a direct invitation to set up simultaneous equations. If you try to guess and check, you're dead in the water.
So the crucial point is that by setting up simultaneous equations using the formulas for the nth term and the sum of n terms, we lock in our variables. We use our Peel framework. Point, establish the 2 formulas. Evidence, substitute -27 and 40 into their respective places. Explanation, carefully solve the simultaneous equations. When you do this, the math resolves beautifully to give us a declining common difference d of -5. Plug that back in, and our first term, a, is 18. Once you have the core DNA of the progression, the a and the d, you own the question. To find out which term equals -212, just plug those core values back into the nth term formula, solve for n, and you find it's the 47th term. This is how top students work. Structure over panic. Every single time.
Now let's look at geometric progressions. These test your ability to handle multiple potential realities because the squared common ratio often introduces 2 entirely valid mathematical paths. Here, the question says the first 2 terms add to 10. Mathematically, that translates to a plus a times r equals 10. The third term is 9, meaning a times r squared equals 9. Again, we have 2 equations, but this time the algebra is a bit spicier because of that squared term. By substituting a from the first equation into the second, you generate a quadratic equation, and as you know, quadratics love to factor into 2 distinct answers. Path A gives a common ratio of -3/5, which makes the first term 25. Path B gives a ratio of 3/2, making the first term 4. You must account for both realities to secure your marks. But here comes the examiner's trap. They will ask you to find the sum to infinity of the convergent progression. Sam would just pick path B because positive numbers look friendlier, and Sam would lose the mark. The link in our Peel framework reminds us to check the rules. A geometric series only converges if the absolute value of the common ratio is strictly less than 1. 3/2 is 1.5. It's too big, so path B is entirely out. We have to use path A. Applying the sum to infinity formula with A as 25 and R as -3/5 yields exactly 15.625. Boom, full marks. Let's transition to Section 3, Mastering Position Vectors, the geometric reality. Stepping out of pure algebra, we now enter the physical space of vectors, or magnitude and direction rule. And hey, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, it is time for an interactive workshop. Let's do a quick data scan challenge. Imagine a 60-second timer is ticking down right now. Look at this complex vector data. You need to extract the core trend immediately. We have points A and B. This scenario requires you to carefully map a point C exactly 4/5 of the way along a known vector path. Remember the golden rule. Position vectors always start from the origin O, so we actually have OA and OB. To find the path from A to B, the vector AB, we subtract OA from OB. 6 minus 2 gives us 4i. 9 minus -5 gives us 14j. So the complete journey from A to B is 4i plus 14j. But point C doesn't go all the way. It stops 4/5 of the way there. To find C's actual location relative to the origin, which is vector OC, we start at point A and add that 4/5 journey. We take OA, which is 2i minus 5j, and we add 4/5 of our AB vector, 4i plus 14j. If you run those fractions carefully, it results in exactly 5.2i plus 6.2j. And this brilliantly illustrates how extracting exact decimal coordinates leads directly to calculating geometric magnitude.
To find the magnitude, or if the straight line distance from the origin to C, we just use the Pythagorean theorem. Square the I component, square the J component, add them together, and take the square root. The square root of 5.2 squared plus 6.2 squared gives us a final magnitude of 8.09.
Time for challenge 2, find the flaw. Examiners love to test your deductive logic by making you prove a shape's properties purely through vector magnitudes. In another scenario, you calculate vectors AB, BC, and AC. You run the magnitudes and get 25, 25, and 20 root 5. Now, if Alex wrote a paragraph saying, the lengths are 25, 25, and 20 root 5, so it's a triangle. Where's the flaw? The flaw is missing the definitive link. Alex loses marks for not explicitly stating why those numbers matter. Because exactly two sides are identical in length, the 25s, the mathematics definitively proves the shape is an isosceles triangle. You must write that concluding sentence. You aren't just doing arithmetic, you are providing geometric proof.
We've arrived at section 4, the interception relative velocity. This is the dynamic climax of the paper, and it is where the most marks are won or lost.
Welcome to Challenge 3's speed writing. We are going to build a perfect Peel framework paragraph for a high-stakes kinematics problem involving a ship, a helicopter, and a ticking clock. Look at this chaotic data. We have a ship leaving port P at 1300 hours. 4 hours later, at 17 hours, a helicopter scrambles from a distant base to intercept it. If you try to hold all these departure times, velocities, and starting positions in your head, you will absolutely crash. Organizing this raw data into a clear matrix, like the table you see here, is the only way to survive the calculation. The table is your shield against making silly, rushing mistakes.
Let's practice extracting information quickly. From the ship's initial velocity vector alone, 7i minus 24j, we can instantly derive its raw speed and its precise navigational bearing. How? For speed, we just find the magnitude. The square root of 7 squared plus negative 24 squared is exactly 25. So the speed is 25 kilometers per hour. For the bearing, visualize it in your mind. 7 units east on the horizontal y-axis, 24 units south on the vertical j-axis. That forms a right-angled triangle. Using trigonometry, the inverse tangent of 7 over 24 gives us an angle of about 16.3 degrees from the south axis. But Cambridge asked for true bearings, which are always measured clockwise from north. So we take 180 degrees, subtract that 16.3, and we arrive at a perfect bearing of 164 degrees. Now here is the ultimate trap of the entire exam paper: the time delay. Because the ship left 4 hours earlier than the helicopter, its time variable must be adjusted. The examiner specifically asks for the ship's position t hours after 1700. Think about it. At 1700, the ship has already been sailing for 4 hours since 1300, so its total time traveling is t plus 4. We must multiply the ship's velocity by this adjusted time, t plus 4, to get its dynamic position vector. If Sam were doing this, Sam would just write t and the entire rest of the intersection calculation would crumble to 0 marks. Don't be Sam.
We are at the final boss. Equating the two dynamic position vectors forces us to find the exact moment their paths collide in two-dimensional space. An interception physically means their I-coordinates are perfectly equal and their J-coordinates are perfectly equal at the exact same moment in time, t. We have the ship's position vector sorted. The helicopter's position is simply its starting coordinate, 409I plus 141j, plus its velocity multiplied by t.
To find the interception, we execute our plan. We equate the I components of both vehicles, the algebra cleanly simplifies, and you'll find that t equals 3. But a master strategist always verifies. We check this t equals 3 against the j components, and it works perfectly. That's your evidence and explanation. For the final link, plug t equals 3 back into the ship's original equation. Remember, 3 plus the 4-hour head start means 7 hours of total sailing for the ship. That yields an interception position of 49I minus 168j. The mathematics flawlessly proves that exactly 3 hours after the helicopter launches, they meet. As we wrap up this explainer, I want you to really ask yourself, are you just memorizing formulas like Alex or rushing like Sam? Or are you truly mastering the structural logic behind these Cambridge questions? We've just proven that the exam coliseum rewards structure. Let's recap the 3 rules of our mathematics success blueprint that guarantee top marks. Rule 1, command word decoding. Rule 2, Peel framework application. Rule 3, time management matrix. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder.
Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.